Okay, so number 15 here from Calculus Chapter 2, we're given this graph and we're supposed to figure out when f is discontinuous using limit statements to help explain why. So let's look at, you can tell from the graph, well, it's definitely discontinuous right here when x equals -4. So if we use limit statements to describe that, well, if we look at the limit as x goes to -4 from the left side, then we're going to get y is close to 1. And it turns out that's also true for the limit as x goes to -4 from the right side. F of x also equals 1. So these together says limit as x goes to -4, from the left and the right, so no plus or minus next to it, f of x equals 1. So that alone doesn't tell me if there's a discontinuity or not. It tells me that at the very least I get a hole there, but maybe the hole's filled in. So the way to prove that the hole isn't filled in is to mention that f of -4, that doesn't equal 1. That just doesn't exist, right? So these guys put together tell me that I have a removable discontinuity at x equals -4. So there's one piece of info. Let's look at this next one here. So this is at x equals -2. So you can tell you have a jump there, but if we just looked at the limit statements, limit as x goes to -2 from the left side, well, that's coming along here. That's close to 2. And the limit as x goes to -2 from the right side, well, from the right side, that's close to 1. So together, these are both finite values, but they're not equal to each other. So I don't get a removable discontinuity. No matter what, you have a jump discontinuity. And in this case, you can tell it's a jump without even knowing which dot is filled in. I mean, it could even be filled in up here instead. It doesn't matter. No matter what, you're jumping from the left side of the graph to the right side of the graph. Okay, the next place where this graph gets messed up is right over here at x equals 3. So let me move this over. So the limit as x goes to 3 from the left side of f of x, so that would be coming along like this. Well, that y value gets close to 1. And then the limit as x goes to 3 from the right side of f of x, that's up at 4. And again, these are both finite values. And it doesn't matter what the actual function is there. No matter what, this is a jump at x equals 3. This one was at x equals -2. So let me shrink that down a little. I'll put that over here. And we got another spot right here at 5. So if we say what happens around x equals 5, well, limit as x goes to 5 from the left side, well, that shoots way down to -infinity. And the limit as x goes to 5 from the right side, that's actually a finite value right here at 1. Well, anytime you have a -infinity or a positive infinity, anytime you have a negative or positive infinity, this wins. So we would say we'd have an infinite discontinuity at x equals 5. There is one last place to kind of examine here. That's an endpoint right there at 6. Let's just say that's 6. X equals 6. Well, if you wanted to check if it's discontinuous there, since it's an endpoint, you really would only check one side. Limit as x goes to 6 from the left of f of x. That happens to be 2. And then f of 6 also happens to be 2. So that just says, as I'm coming at it from this side, the first part says, around 6, the y value is 2. And when I'm at 6, it actually fills it in. So since it's an endpoint, you'd actually say continuous at the endpoint. The only way that it wouldn't be continuous is if it went off to infinity, or if it did something like this. Like that instead. So, okay, and that's it for this problem. Hope that helps.